We're now going to leave the study of hydrostatics, that is, fluids that do not move, and we're going to start to study fluids that move because we're mechanical engineers and that's what we do. There are three ways to study moving fluids. One way is experimentally. So obviously you can go to the lab, as you will, and you will study fluids in actual motion, take measurements, and figure out, in that way how fluids actually move. So experimental is number one. Number two, the one that I like the best, is differential equations. So differential equations, we will derive the very precise equations that govern fluid flow down to its smallest level, and then you can solve any flow. But this is extremely difficult. The differential equations that govern fluid mechanics are partial nonlinear differential equations. They're extremely complicated. They can only be solved with paper and pencil in some very, very simple situations. Some of those are important situations, but nonetheless, there's so many fluid problems that cannot be solved with paper and pencil. So a lot of times, differential equations, they're solved using computers. That's what COMSOL does. You'll be using COMSOL in the lab as well. And we will definitely be making progress on that. And differential equation analysis is going to be what really gives you insight into what fluids really do and how they really behave. But before we get into that, we're going to take a look at the third solution method or third study method for studying moving fluids. And that's a control volume analysis. And so that's what we're going to get started on today. And so you're familiar with control volume analysis from thermodynamics. We're going to take a controlled volume of fluid and we can analyze it. It's a largish volume. This is not a smallish infinitesimal control volume. That's what we'll use for differential equations. This is a macroscopic volume, like a nozzle or a tank of fluid or a swimming pool, something that has real substantial size. And by studying what goes into it and what goes out of it, you can sometimes get important engineering results. This technique, the control volume analysis, it only works for a very small set of problems. So it is certainly not a universal technique for solving fluid mechanics. It also tends not to give you very much insight at all into the particular nature of the flow. We'll talk about what I mean by that as we see it. But it doesn't get into specifics. Control volume analysis is going to give us large, sort of macroscopic answers to certain problems. But it is important because some of those problems are highly relevant to engineering. And so even though control volume analysis lacks a lot, it is sometimes from an engineering point of view very, very helpful because, as I said, this partial differential equation type of solution is extremely difficult to use for many, many flows. Experiments, of course, are not practical in many cases. Sometimes you want to know something without running the actual experiment. So the fact that even a small set of problems can be solved using a relatively simple, algebraically based control volume analysis is really, really helpful at certain times. So that's what we're going to start on. And I'm going to remind you what a control volume is. It is usually a fixed volume, but it does not have to be. A control volume is a clearly identifiable region of space, and that's going to be your system or your control volume. In thermodynamics, we said control volumes basically we're always a fixed volume. That doesn't have to be the case. Control volumes can move as long as you know how they're moving. But in most cases, we will in fact study fixed volume control volumes. So that's going to be what we're going to start on in the next lecture. We're going to apply that to conservation of mass.